So what I'm going to do today is to walk through a collection of tips for trying to write fast Wolfram language code. Wolfram language is very much optimized for trying to work at the highest level possible so that you can be as performant as, and quick to write the code. But often that hides some of the technical details about the way things are done behind the scenes that makes it a little bit harder to optimize. So I'm going to hopefully give you the information you need to be able to write code that is both easy to write but also fast to run. I'm also going to go through a range, within that I'm going to go through a range of different tips from quite beginner ideas at the start of the webinar, and towards the end we'll get to some more advanced ideas, although I will assume some basic Wolfram language knowledge to start off with, but all my examples will be very simple, so if you don't know Wolfram language you'll be able to guess the syntax. So we're going to go through some general advice first of all, then talk about some data structures, parallelization, and ultimately the route to highest performance is code compilation. And if we have any time left at the end, or we're short on questions, then I'll maybe talk about a few other smaller hints and tricks. So let's start with the most general advice. And if there's one, there are two pieces of advice that I would always give. The first one is to use built-in functions. Now, what I mean by that is that Wolfram language is very large. There's 5,000 functions available within the system. It's quite hard to know all of the capabilities of what's there. So very often I find when I review other people's code is they've reinvented functions that are already in the system. And it's almost always going to be slower to execute code that you've written yourself rather than using a built-in function where we've spent lots of time optimizing it and using the kind of smartest tricks behind the scenes to get the best out of the function. So one specific type of that, and this is more of a style of programming I see a lot, is using indexing as a way of coding. If you're working with low-level languages like C or Python, then it's a very common thing to handle the data by counting through one item at a time and constructing a new vector based on each of the elements processed in some way. So here's that kind of style of programming. My example here is to generate some random numbers, and then I'm writing a typical kind of procedural do loop type code here, which is to have some temporary value, and I'm going to count through the data, the ith element of the data, with I going from 1 to the length of data. Could have done this with a for loop, but the same kind of principle, and I'm accumulating a total as we go. So this is a low-level way of adding up the values of a list. And you can see here for this million items, it's taken 0.7 seconds according to the absolute timing function, and has produced this number as the result. Now, of course, as you would expect, this one's fairly easy to guess, there is a total command within the Wolfram language. So compared to the low-level code that I've written to do that, reaching into the data over and over again to take out the ith element, just operating on the data as a whole allows it to do much more behind the scenes optimization, and we get 0.003 seconds. So can't quite do the arithmetic there, but that's about 200 times faster than writing the do loop approach. So that doesn't totally solve the question for you of how you figure out what the commands are that are available to you, but always stop and think if it seems like a typical thing like adding up the value of a list. If you're starting to write loops to solve that, then the chances are you've missed some built-in function that should exist. Now, even when there isn't a built-in function, this idea of indexing items one at a time is still a bad thing generally. You usually want to write code that moves the data around as a single item, not as a whole bunch of separate items. So in the case, for example, of taking the sign of each element of a data, which is what I'm doing here, this would be your low-level kind of traditional language approach of make a new vector where the ith element of the vector is the ith element of the old data operated on by our function, and we count through the data one item at a time. And that takes nearly 0.2 of a second to do those million sign calculations. But at a functional programming style, we can use commands like map that we don't, first of all, from a programming point of view, we don't have to do the bookkeeping ourselves of knowing how many items there are for working out the length and starting at 1 and going to the last item. We can just say map to the whole lot. But also map is designed to expect an array, where a table could be doing anything to make tables of values. It's hard for it to know that it might be about to receive a table of data as the input, whereas map expects that. Map is supposed to operate on lists or arrays or similar kind of sets of data, and so it's much more optimal. It's 0.04, so that's 5 times faster than the item at a time. Now, actually, in this case, because it's quite simple, we can do even better, because Sign itself already knows how to handle lists. And so not even bothering to explicitly state that we're mapping over, just saying take the sign of the list of data itself is another 40 times faster still. But that's only because we're really operating right down at the built-in function level. So as a general rule, the fewer functions in your Wolfram language code, the better when it comes to performance, as well as being better for writing and maintaining the code. Now, sometimes that gets also a little bit more subtle. It's we can do more with some of the more hidden arguments of functions. So I've got the simpler one first, because it's a really common case I've seen many times, is that here I'm making a table of random numbers, random reals from 0 to 1, and we're going to have 10 million of them, and we'll make that table and measure how long it takes. But random real itself has multiple arguments. Its first argument is the range of numbers that it's randomizing over, but its second optional argument is the number of numbers it generates. It generates 1 by default. So if I do, if I just copy this out here and do random real 1, you see we get just 1 number. But if I give it a second argument, it'll generate a list of those. And as with most things, when we have built the thing into the function by having a second argument for the number of random numbers we're generating, here I'm just using the second argument, again, that will be much, much faster. It can anticipate a lot more about what it's trying to do if you haven't taken that information away from the function and wrapped it in some outer function that it can't see. I've included one more example, which is much more complicated example, and you'd be forgiven for not learning these details of functions because you can get away without it. But if you want performance, then reading all of the small print about functions, it matters. And one of those often ignored optional arguments is level specification within particularly list and data type operations. So I'm making some slightly differently structured data here. This time, I'm going to make a 3-dimensional array, 100,000 by 2 by 2. And here's the kind of first 2 elements of that. So you can see we've got several levels of lists building up here. It's high dimensional data, or higher. And what it actually represents is a list of matrices, because the way we represent matrices is a list of lists. So you could think of this as a very long, thin rank 3 tensor, or you could just think of it as a list of 2 by 2 matrices. So my task in this case is I want to turn these 2 by 2 matrices into lists of 4 numbers. So conceptually, the simplest way, and probably the way I would write it myself as I knock out code, is to say flatten is the command for getting rid of all the structure from a matrix. It'll turn a matrix into a list. And if we do that, if we map that across the data, we'll flatten each of those matrices and get our lists of our data out in the new reshaping that that we would want. Now, actually, there is a command array reshape, which might work well here, but I haven't actually time to see whether that does better. But the example I was going to show about level specification is that flatten itself, its default is just to squash all of the shape out of high dimension data into a flat list. But actually, it takes some complicated second arguments that can tell you what levels to squash together. So here it's saying, I don't want to flatten at level 1, but I want to squash levels 2 and 3 together. So that has the same effect. It's a little bit more cryptic than saying map flatten, but now we're, instead of having 2 functions, the map and the flatten, we now essentially have 1 function, flatten, and in accordance with my claim that usually fewer functions is better, we see a higher performance. So always try and see if you can eliminate code and find the fewest number of high level functions or highly specified functions to do the work, rather than filling it in with just more code. Okay, my number 2 piece of advice, if you're going to drop out early, this is the second one you must know about the Wolfram language, because I see this over and over again with performance, is not understanding the numerical model of the Wolfram language. And in particular, we want to use floating point numbers as much as possible and as early as possible if we want to write fast code. So let me explain what I mean by that. There are several number types in the Wolfram language. So if I enter 1 divided by 3, that's an integer 1 divided by an integer 3. And because integers are exact, the only way that we can represent that exactly, we don't want to kind of approximate without permission, is to represent that as a fraction of 1/3. There's also ideas of high precision numbers. So I can enter 1/3 backtick 200 to say I want to work in 200 decimal places, another kind of number. But if I ask for the numerical value of something with n, so I can say what's the approximate numerical value of that high precision number, or I could say, if I go back to this third, what's the approximate numerical value of that, then we get what's called a floating point number, a machine precision double within the system. And also, if you use a decimal point anywhere in a number and don't follow it by more than about 16 decimal places, which will tell it that you're trying to be very precise. If you have fewer than 16 decimal places after a number, that will also tell it to work immediately in machine precision numbers. So that's the different number types. But the key thing here is that machine precision arithmetic is much, much faster than integer arithmetic in the Wolfram language, and much, much faster than kind of complicated expressions like, okay, 1/3 isn't that complicated, but rationals or complexes. We want to work in floating point numbers as much as possible if speed is what we care about. Now, the downside is floating point numbers are only accurate to 16 decimal places, the same as any standard numerical language you'll use. And so they're less accurate than working with exact or high precision numbers. So you have to worry a little bit more about whether you've got stable, accurate results coming out. But in return, you get the higher performance. So let me show you some examples to make sense of this. This is a decent example of this. This is a Hilbert matrix. Actually, let's just make a smaller one so you can see the structure here. I'll just do 15 by 15 first of all. So it's a matrix. And if I make it look like a matrix, you'll see it's a set of fractions that get smaller and smaller as you go away from the diagonal in the matrix. So it's actually a classic ill-conditioned problem. I'll put it back to the 150 by 150 size. Now, I've got two very similar looking bits of code here. I want to find the numerical determinant of that matrix. That's my challenge. And in one of them, I say, let's take the determinant of that matrix. And then, oh, by the way, we want that numerically. And in the other, I'm taking the numerical version of the matrix and finding its determinant. Now, they seem almost identical. And in fact, the answers we get back, if I take the semicolon off the end, we'll see the result, should be basically the same answer. And in fact, they come out, as far as I can see, exactly the same answer. But you can see here the difference in performance, that taking the determinant first is massively slower, 200 times slower than numericalizing first. So this is what you always want to do, is to get floating point numbers as early as possible into the calculation. Now, the reason for that is if I just do this outside of the n, so we can see what the intermediate calculation is, the first thing it had to do was to calculate this fraction. And you can see this is a really complicated fraction. And there's the numerator, and here comes the denominator. And it's worked that out exactly and then approximated it. So that's a lot of work that we didn't really care about in this case, to work out that exact fraction beforehand. And that's where all of the timing went, was doing the exact fractional arithmetic of multiplying rationals together and keeping track of this ever-growing very long number, which we then threw away all of that detail by saying numericalize. In the case of taking the numerical version first, then det just does that numerically, not with these exact fractions, and that's a much faster algorithm. In fact, we probably could have done better here by starting right at the beginning with by putting a decimal point in, so that we generated the matrix in the first place as floating point numbers. And now if we do det m and time that, we might even see a slight improvement over not having to numericalize the fractions in the first place. Don't know if that was measurable. No, in fact, some other noise has gone on to make it very slightly slower. But in principle, this was the slightly faster way of doing it. Now, that isn't just about when you're floating numbers around within the system. There's a lot of functions in Mathematica that have a numeric and a symbolic equivalent. Classic one is integrate, where there's this integrate command, and there's an accompanying nintegrate. And they're done as different commands because they are really different tasks. One is to find a symbolic integral, which may turn out just to be a number, but it's doing it by symbolic techniques, and the other is doing it by numerical techniques of sampling it or creating slices, or Monte Carlo methods. There's a whole bunch of methods in there. But again, this makes a big difference to the approach, because if I do that symbolic integral, to get the exact answer symbolically is quite complicated, and it's taken a long time. It's nearly 7 seconds, which I can then find the numerical value of. But saying that I don't care about that, just sample it from the beginning, we get very fast performance. So even though the answer of doing n of integrate is the same as n integrate, it's much faster to use the n functions first if all you care about is numerical results at the end. Basically, don't do more work than you care about for the answer you're trying to achieve. Okay, so they're my two biggest things, particularly for beginner users of the Wolfram language. Let's dive a little bit deeper now. There are two basic core data structures for data within the Wolfram language: lists and associations. Now, the idea of lists is that they are indexed by value. So a list might be some numbers like, or well, not necessarily numbers, any old contents like A, B, C. And when I say index by position, I can say what's the second item in that list. So that's how we index things, by saying where they are, or how far from the beginning, or how far from the end, or some range of numbers for the positions they're in. And then we have the association structure, which is indexed by name. So we got a shortcut bracket, but it's called association. And in this, we have named values like first and second. And so they're key value pairs, like a dictionary in some languages, or kind of more similar to data structures like JSON. And here, if we want to index those, we index them by the name, not by, well, we can index them by position as well, but the idea is that we index them by name. So I can say, what's the thing that has the first named key on it? And the one with the key first was A. So they're both very general. They're both understood by thousands of the functions in the Wolfram language, but they do have different properties about memory and performance. The basic difference is that these are the indexing for association is done as a hash table, which means that things like insertion are an order one cost performance. Either it's a constant time operation to insert or to append to, whereas lists require a copy over. So that's the big difference from a performance point of view, is that modifying large lists, because they are immutable, takes a proportionally longer time for larger lists. Now, doing other processes on them, actually the list can be faster because they've got less memory footprint, because they don't have to carry around all these key names in the data structure. They can just take that implied. But one kind of common pitfall is accumulating data. So you'll often see this paradigm in people's code, which is I'm making a bag to put some data in. It's going to be empty to start off with, and I'm going to do something many times, in this case, random real, and I'm going to append to that bag onto the end of it and that random real number, and I'm going to do that 50,000 times. And now, obviously, you can already see that I could have done random real 1, 50,000 to achieve the same aim. And then I'm just going to, for display purposes, I'm just going to take the last 3 elements from that list. So what we get here is we'll see a list of 3 items, the last 3 elements of our list. And it's taken really quite a long time to do that. And the reason is that this append to operation is pretty expensive on lists. It's just a kind of standard pitfall to be aware of this order n computation time on appending for lists that should be avoided at all costs. Now, for small lists with 5 or 10 items in it, really doesn't matter. But if you're building up a large amount of data this way, then by the end we're having to copy 50,000 bytes of data every time we add one. So here's the same code now, or almost the same code, using associations as a data structure. I set up my empty bag. this time I've created an index for the key name, and each time I'm going to append to the data the random real, but it's going to be indexed with a number which is going to increase. So my association is going to be 1 goes to some number, 2 goes to some other number, 3 goes to some other number. So I'm actually recreating the effect of being able to index by position, because these keys have to be unique, so I have to keep changing this. And what we get back at the end of it is an association with the keys that we may not care about, but they're there to give it structure. But you'll see here that because of that constant time addition, then actually the accumulation is much, much faster. Now, of course, in this case, you do random real. There's also a sow and reap mechanism, which is pretty fast as well, that allows you to work with lists, but without falling into this copy trap, because sow and reap collects all the data up once at the end of the operation. So that's also worth looking at. The slight downside here, I should have run this at the time, is that the association form takes a lot more memory because of all these keys that have to be stored, and the structure is less efficient as well. And it's also generally true that if it wasn't for this difference between the two, that minimizing memory is also a good thing for trying to minimize computation time. But in this case, the benefits of hash table lookups outweighs it. Okay, now, so those are our two most general data structures, the list and its extrapolation into being lists of lists and lists of lists of lists and so on, and associations, which themselves can also be nested too. But we also have a kind of increasing collection of more specialized, more optimized data structures. They're not as general, they're not as useful widely throughout the system, but they bring with them performance benefits. So the more you know of these and use them wisely, then the better performance you can get. So I'm going to introduce a few of these here. The first one you don't have to know too much about because it's pretty much automatic in the system. And that is something called a packed array. So to make sense of this, I'll give you the example first, and then we'll talk about what's going on. So here I'm using random real to generate a million random numbers, and they take 8 megabytes to store in memory, and here's the first 3 of them. I'm going to take that same data set, and I'm going to stick another number on the end of it using append, and I'm going to store that in data 2. Again, append is relatively expensive, but we're only doing it once, so it doesn't matter too much. And you see here that the data 2, even though it's only 1 item longer, suddenly takes 3 times as much memory to consume. So the reason for that is kind of invisible to you, because in fact, if we take, let's take a look at the new data we've created. If we take a look at the first 3 elements of that, from a user point of view, there's no difference. It's whatever's happened here has happened completely automatically and behind the scenes. Now, the reason is that when we did random real at the beginning, random real can be clever and says, okay, I know that every number I'm going to get back is going to be a real number. And so it can make a decision to automatically, instead of using the regular storage mechanism for arrays within the Wolfram language, it uses this packed array behind the scenes. And what effectively that's doing is, instead of saying, here's a real number, its value is 0.86, here's another real number, its value is 0.2, it says, it restructures that to say, here comes some real numbers, and their values are 0.8, 0.2. So it doesn't have to keep saying this is a real number and over again. And that's only true because the data is all the same type and was predictably all the same type before it started. And when I put in an integer, that broke that rule. It can no longer say these are all real numbers. It now has to say for each number, this is real, until it gets the last one when it says this is integer and its value is 1. And that extra memory overhead is what's made it treble in size, and it also makes it slower to operate on. I don't have an example of doing an operation on here, but you can imagine that with more memory to move around, more data to move around, it's slower to use the unpacked array. So as I said, very often those things are automated if you use things like random real, or often with things like table, if it can determine that the argument of the table is going to be real every time, you'll get a packed array automatically. There are some times where you can't do that. For example, importing data from a file, it can't make that assumption up front because it doesn't know what it's going to see until it's read the file. And so in those cases, there are a couple of developer functions that allow you to optimize that when the automation fails. And the two functions you need to know about are developer packed array queue, which tells us whether or not it is in a packed format. And we can now see explicitly that while in every respect from a user point of view, all of the functions I might apply to those all work exactly identically, internally behind the scenes, they have a different structure. And we have this ability to coerce between them. So there's this developer to packed array that allows us to take this unpacked data, and we're going to make sure that it's all numerical. Or there's a second argument to packed array to say, I want them all to be machine reals. And then I've made something that is now packed. And then computations on that going forward will be faster. So this is something you should consider if you import a large CSV file or similar into the system, is to force it into a packed status if you're going to do a lot of statistics or linear algebra type operations and you want them to be fast. Right, getting more specialized still, there are certain classes of problem where you're working with arrays of data, but the problem is what's called sparse. And so sparse problems are ones where the large majority of entries in the array are 0. Or more generally where they're the same, but typically the most common case is where they're 0. So a good example of this would be if you have the road network of a country, you can represent that as an adjacency matrix that there's a number to say, for 1 to say my village has a road connecting it to the next village, but a 0 to say that there isn't a road that directly connects it to London or directly connects it to some other distant city. So since most places in the country are not directly connected by a single road to most other places, you end up with a matrix that is mostly zeros. And you don't want to store all of those zeros, and you don't want to compute with all of those zeros because zeros usually don't do very much. When you're adding up data or inverting or transposing matrices, then just being able to ignore all the zeros makes things a lot faster. So we have a representation for that. It's called sparse array. And the idea is that you explicitly state the items that are non-zero. So position 5 in the array has the value 10. So this is positional indexing. If this was going to be a matrix, then this would be position 3, 5 or something, say row 3, column 5. And then the second argument I've got here tells it how many elements there are in the array. So I've got 1 trillion elements in this array. So here it is, having declared it. It computes into a slightly more optimal form internally, but basically nothing really has happened. But if we look at this, the amount of data required to store this thing is quite trivial, 680 bytes, which is mostly set up. If I had 2 non-zero elements, maybe the last element in the array is also non-zero, then the amount of data required to store that has, in fact, not even gone up at all. It's managed to store it in exactly the same amount of data. So a lot of that 680 bytes was overhead. And basically, you end up with the amount of data is kind of in proportion to the number of non-zero elements rather than the size of the list. But for all other purposes, for standard operations that are supported at least, which is not everything in the system, we can do things like what's the length of this or the total of that. So total, again, will be very, very fast because it has very little work to do compared to if this was a dense array where it has to visit every one of those zeros and add 0 to the total to see what that does to it. Now, if there's a handful of operations that are highly optimized, like linear solve and determinants that really know what to do with this, in other cases, you're going to have to, at some point, convert that into a dense representation. And the way you do that, like most changes of type into a more standardized type in the language, use normal, and then it will make a packed array or regular array, filling in all of those zeros. Now, you can very easily type something in here that will just simply run out of memory the moment you try and unpack it. So you may find that's not a feasible thing to do in practice. I don't know if this one will work. I've already done the timing here of adding it all up. But if I try and create the unpacked version. Took a few seconds to unpack the thing. That takes 0.4 seconds compared to 1/10,000th of a second that it took to process the sparse version. So we want to work with the sparse versions whenever we can. I'm just going to return that memory here. Let's remember those trillion numbers. Right. There are also, I'm not going to show examples of these, but it's worth being aware of them, that there is a whole collection of even more specialized matrix or array type structures that go by the name of things like symmetrized array or upper triangular. So upper triangular matrix, for example, is one where it's all zeros below the leading diagonal. Block diagonal matrix is where it's mostly zeros apart from rectangular blocks that are centered on the leading diagonal of the matrix. Now, again, these all just allow you to represent the data in a more compact way because you're not having to declare all of the zeros. And they also come with an accompanying collection of specialized algorithms. So there are certain linear algebra operations that there are known algorithms for being much, much faster on processing a lower triangular matrix than a regular matrix. And so if you're in the kinds of problems that lend themselves to triangular matrices or block diagonal, for example, certain solutions to differential equations naturally form these shaped matrices, then you'll get a sort of 2, 3, 4 times performance improvement compared to the dense version. Now, beyond that, and now we're entering a world of more kind of computer science type data structures, that there are data structures that have been highly studied by computer scientists that are really optimized for different kinds of operations. And we have a general mechanism called DataStructure for representing these kinds of different data structures. They are not anywhere near as general as the things I've been talking about up to now. Typically, these data structures support only half a dozen, maybe a dozen, sometimes as few as 3 or 4 operations. But if the operation that you're wanting to do with the data fits into that set, they can be much, much more optimal than using a general data structure. So let me show, this is perhaps the simplest one that I could talk about. A queue data structure. So a queue is a data structure that you can put items into it, and you can take items out of it. And you can see here the idea of create data structure is that you tell it the data structure type, and now it's created an object that is known to represent a queue. So there's some internal structure here that I don't really have to worry about that is optimized for queue type operations. Now, this is the full set of operations that you can perform. You can make a copy of the whole thing. You can empty the queue. You can convert this to a list to get out the elements in it. You can check whether it's empty, see how long it is. But this is really intended for looking at the queue or pushing and popping things onto the queue. So pop will remove the first element of the queue, and push will stick something onto the back of the queue. So we can have people join the queue and people leave a queue if it was representing an actual queue in the real world. And then the last operation makes just a little quick visualization of it. But the key thing here is that while the number of operations you can do is really limited and basic, if you're worrying about queues and you're doing things like pushing and popping, these have been designed so that they are, in this case, constant time algorithms. So these are all these data structures that are listed up here at the top that we support. They all come documented with the time performance of the operation. So if we compare that to, so we can use it here. This is the data structure I just created. And if I push one into the queue, I now have a queue with one thing in it. I can stick something else into the queue, and it's got 2 things in it. And now if I pop, I'll get the thing that was first in the queue as the first out. That's the definition of a queue, is first in, first out. And pop again, and I'll get the thing that was second in the queue. And I guess if I pop again, I will get a failure because the queue is now empty. So pretty basic, but where it becomes useful is for performance. So let's look at how one might do this. I've written a very sloppy version of a queue implementation in low-level Wolfram language. My push operation uses append to, which I've already warned you against, onto a symbol called queue. And my pop operation gets the first item out of the queue, and then resets the queue to the rest of the queue. So that's implementing the push and pop type operation. And here I'm going to apply it on some new queue where I'm just doing some computation to decide periodically whether I'm going to pop or push. So basically, I'm going to count through 1 to 50,000, and every time it's divisible by 3, I'll pop an item out, and if it's not, I'll stick an item on. So the queue will get gradually longer. And we'll run that and see the time. And I didn't run the code first to define it. Let's do that again. So here's my result, 25,000, and it's taking 0.97 seconds. Now here's the same code now using this create data structure. I create the data structure that sets up my empty queue. Here's my code. I'm just using those named operations, push and pop, instead of the functions that I had to write for my non-built-in queue. And then I'll return the final value again, or the one at the front of the queue at the final step, and run that and see the timing. And you can see here that we got 20 times faster on this pretty basic bit of computation. Now, the key thing with these data structures is you've got to kind of anticipate the usage. And it's worth spending a little bit of time just browsing the different data structures and understanding what their reason for existing is. Some of them are there because people who have come through a certain computer science background just like to think that way. Some of them really lend themselves to certain situations. And I've got a couple of examples of the slightly more richer examples of data structures and some situations that they help in. But the key thing here is to think about what are you going to do with the data once you've got it, and then picking the data structure that makes that as fast as possible. If you're going to do lots of really general things with it, then you're going to want to be in lists, because you'll soon find yourself converting out of the specialized structure. So here's one of the slightly more exotic ones, a byte trie or a byte tree, depending on your preferred pronunciation. And the easiest thing here is if I set one up by inserting some contents in and then making a visualization, and then it's easier to explain. What it's doing is basically creating a tree-like structure where shared starting values are recorded only once. So because I've got A, B, and ABB, and ACB all sharing an A, I only need to mention A once, and I've got ABB and ACB underneath the A, and likewise underneath the B, I've got BBC, and I've got a root node here as well that groups all of that together against another start value. So this is quite a memory efficient storage if you have a lot of commonality between the data, but it's also a very fast for looking up if you are searching downwards. So if you want to find all of the things that begin with A, you can just go down the tree that begins with A, and everything under that is now your solution. So for forward searching, it's a very, very fast data structure to hold your data in. You don't have to visit every item and say, does it begin with A? And so that makes it very good, for example, for text string completion. And that's the example I've got here. I'm going to create a byte tree data structure that can accept items from A through to Z. And then I'm going to insert into that a whole bunch of data, and I'm going to just scan that over a dictionary lookup that I've cleaned up a little bit. So I'm taking the dictionary, I'm removing umlauts and accents. I'm making things lowercase just so that I can treat A and capital A the same thing. I'm removing a bit of punctuation with string replace, and then I'm going to insert every single word into the byte tree. So that takes a few seconds, a couple of seconds to set up the data. But once I set that up, I now have this byte tree where I can search for begins with very fast. So here's all the words within that begin with BRIG. So we've got brigade and brigades and brigadier and brightness and so on. And that has taken, what is that, 10th, 100,000, 2 10,000ths of a second. So 1/5000th of a second to search the English language for words beginning with brig. Now we do have a built-in dictionary lookup command within the language already. So you don't have to do this unless you want performance. And here's the equivalent command. But because dictionary lookup has to worry about all kinds of string patterns, I might be searching for contains or starts with an A and then has a B somewhere within it and then has the last two letters being ZZ or whatever. It's a much more general thing. That generality comes at a price. And so you can see that we've ended up with 0.008 seconds. So yeah, about 80 times slower 40 times slower maybe to have done that computation. I show you just one more and then we'll move on to a different topic. So here's one more specialized one, is a Bloom filter. If you've studied computer science, you'll probably know all of these things, but they're mostly not very hard to understand. Bloom filter comes with a very specialist operation, which is a could contain operation, which is a probabilistic non-guaranteed check for membership. So let me try and remember which way around that is. It can guarantee that an item is not in the set in fixed time. It can say whether it probably contains the set, but it doesn't guarantee that it does contain the item if it returns could contain. If it returns true, it doesn't guarantee that it does, but it probably does. But if it says false, it guarantees that it doesn't. And so we can do the same kind of thing with setting up a Bloom filter with the same dictionary. And you can see the code I've used here is exactly the same, except I've used Bloom filter instead of byte try. But now I have this could contain operation, and I'm giving some letters to say, are there any words that have XERT in the dictionary? And it says guaranteed not in an incredibly fast time. So sometimes things like auto completion, when you're typing into an input field, you want to say, is this something that's likely in my data set so that I can auto complete it, or prompt the user to say, would you just like to search for this? That can happen fast enough to populate a user interface as you're typing. The basic idea of parallelization is that we want to, if we're doing the same thing many times or some independent thing many times, then we can utilize multiple computers to work at once. So in many cases, the Wolfram language is single-threaded. So even on one computer where I have multiple cores, I'm only ever using one core. Now, that's not true for some of the numerical operations and some things that have been optimized internally, but typically for example, symbolic computation is nearly always single-threaded. And so the idea of the parallelization is you have a task manager, which is the Wolfram language engine that you're kind of directly talking to, and it takes the job and it breaks it into pieces, hands them out to workers that could be on your computer if you have a multi-CPU, multi-core computer, or they could be other computers that are idle around your network that you have permission to access. And it hands out the instruction. All these work at the same time, and the manager's job is to pull in the answers as they arrive, collate them, and then return the collated result. So just like an office manager hands out work, tries to do nothing himself, and takes all the credit at the end. So there's a small set of these that mostly mimic single-threaded operations. So we've seen do loops. There's parallel do for a parallelized version of a do loop. There's parallel table for a parallelized version of a table. There's a few more specialized things like submit and try, which allow you to take a little bit more control. But here's the basic idea here. I'm going to do one of the simplest things here, which is I'm going to do I think I actually really have the wrong argument here. Example here, the diagram says parallel evaluate, which is to do 4 completely independent things. I'm actually going to do parallel table here, which is parameterized. But the same basic idea. I'm going to work out some prime numbers from 15,000 to 15,100, and we're going to do them in a regular Wolfram language way, which is a table, and we'll just try those numbers one at a time, 100 of them in a row. Primality testing for large 2 to the power 15,000 type numbers is relatively slow, so it's taken 10 seconds to compute through this computation. But what I can do now is I can tell it to launch some workers, and I'm on quite a big machine here with 24 CPUs. So it's launched 24 Wolfram engines, and it's given me an object that allows me to talk about them, to reference them. And now if I take the same operation here and change it very slightly, so let's just copy that up and do parallel table, it'll now divide that job up into 24 different pieces, and one to each of those 24 workers. And then when the last of those workers answers, it's got its answer back. And you can see here that we've achieved some efficiency gain, about 8 times faster, I would say, 7 or 8 times faster. So in theory, if you've got really optimal problems, that could have been 24 times faster. But there's some overhead that's lost in the communication, waiting for the slowest kernel. You've got to send the answer, you've got to read the answer back. So you rarely get 100% efficiency in distributing things. And I guess I could do a version of that just to make the point clearer here, is I'm going to get back each of those answers labeled with the ID of the kernel. And so you can see here that worker number 7 produced the first. Oh, hang on a second. What am I doing here? I'm finding the factors. I'm finding the number of prime factors. Okay. So in fact, there were 7 prime factors found by the first task, and this was it was labeled as task number 1. So you can see it's actually been pretty efficient here. It's given all of the jobs to different kernels. But if I made this list a bit longer, you'll see that the same workers get asked to do more than one thing sometimes. So it's doing a little bit more work here. And we can see that worker number 1 worked out the first 2 problems. And after it finished, it was asked to solve another problem because it reported back in and there was still work to do. So you can see here this kind of idea that it breaks it up into chunks that are optimized. It tries to hand out as much as possible in the chunks at the beginning, and it cycles through those as the answers come in. These remote workers, we have some tools as well to make it easy to set those up. So if you have a computer lab that is idle at night and you want to run a 200 computer parallel job, then we have tools that allow you just to configure that on your computer, and with admin privileges on those machines, you could just sit at home and fire up a 200 CPU network. If you're kind of in a university type environment where those kind of resources are lying around. Okay, let's now get on to the most advanced topic, which is function compilation. One of the things that is a guiding principle for the Wolfram language is that it's very weakly typed. So when I create some data, I can put into that a list of things that could be all kinds of things without having to pre-declare how long this list is, but it has a real and it has a complex, and maybe it has in it an image, and that list structure and had an image, then that would work just fine within this function. Maybe I could do one which is example data, not try and access the camera, test image, some test aerial photo in there instead. So our data structure can be really quite general, and if you give functions arguments that are very general, it'll try and do sensible things with them. So here it couldn't figure out how to add an image to a complex number, but it did figure out to add the real and complex number. So it's able to handle that without complaining, without having to be warned that there's going to be images or documents or time series in the data. And that's a really good thing from a usability point of view for writing fast code without high expertise that does really powerful things. However, it comes as an overhead when it comes to execution, because it's constantly having to say, what kind of type is this argument, and which algorithm do I have to switch to in the case of combining a real and a complex, and can I find an algorithm for adding a complex to an image, and all of that constant testing of types takes time. So the idea of the compiler is that it allows you to, and I guess here's an example I have of that, where that starts to matter. I've got a function, and I'm just changing my notation here to use function notation within the Wolfram language. It says the function takes 2 arguments called arg and n, and it's going to repeatedly, using nest, apply the sign to the initial argument n times. So this is going to be sign of sign of sign of sign of sign of 10.1 5 million times. But that will just work quite nicely, even if this is a complex number. So I've made this approximately the same number, but in complex plane. It's gone a bit slower as it has tried to use complex arithmetic version of sign, but it's handled it. But the idea for the function compile is you can tell it in advance that you know these arguments are going to be certain types. And that does several things. First of all, it allows it to stop having to test, apart from once when you call it at the beginning, just to make sure that you've not reached the expectation. It allows it to rewrite your code and optimize it. So there are various sort of simplifications it can make if it knows what to expect. If it knows it's going to get a number that is going to get called on later, then it knows it can only has to calculate that once. It doesn't have to calculate it repeatedly. Whereas if it knows that that's dependent on something that might change, it knows it can't shortcut there. And all of these compilation type shortcuts allow you to end up with a much more efficient piece of code. It also gives you another benefit, which from a user point of view, which I'll mention in a minute, which is about kind of correctness of the code as well. So here's the same code rewritten. I've got the same function as I had before, a function with the arguments arg and n, and it's doing the same nesting operation. But this time I'm going to annotate the arguments with what to expect. Now within function, actually, I could have done that right here, and it would have simply ignored it. So I could actually just have written this function the first time this way, and we get the same result because within function it just ignores it. But when I then wrap FunctionCompile around it, it takes this function and it thinks about it. It thinks about what the consequences of those assumptions are, and what it will then do, it's actually making a symbolic representation of the code. It's applying a whole bunch of type inferencing to figure out for each step in the computation what the type is likely to be that comes out of that. Is then converting that into LLVM, which is a technology, I think it's low-level virtual machine, which is a compiler technology that is a very active research project. And then it's using that to generate the machine code, the assembler and machine code for the CPU that I'm sat at right now. So it's actually ending up with machine code for, and I don't even know whether I've got an AMD or an Intel chip here on this machine, but it will use the right optimizations for that target. I can also tell it that I want to cross-compile, say I want this for a Mac ARM CPU, and tell it those things, but by default it'll compile for the machine that I'm running on. And what I end up is a compiled function code object. There's a lot of complicated things in there, basically pointers to the library and representations of the assembler, but I've just stored that and I can reference that, use that as if it was a built-in function now. So now when I do this CF on the same operation, the sine of 10.15 million times, it's now running that in optimized compiled code directly on the CPU, linked invisibly into the Wolfram language so that I don't have to know about those details. And you can see here what's our timing performance. We had 0.14 seconds in the top level code and 0.04, so not a dramatic improvement, about 3 times faster in this case. But then this was a very trivial piece of code, and as your code gets bigger, the optimizations can add up to give you, better improvements. And here's what it's doing behind the scenes that I just talked about. That if I ask it here with FunctionCompile export string to show me the LLVM that gets generated, if anyone's familiar with LLVM, this is code that's been written automatically from that function. There's also some references to, maybe not in this one, if you are using functions that cannot be compiled, then the system will link back into a Wolfram engine so that the code doesn't simply fail. It will do the compile bits in the compiled code, but then it'll call home, as it were, to get the hard work done for, say, symbolic computations that are not yet compilable. And then here's the final step that this is the assembler now for Windows on an x86 64-bit architecture, and this is the machine code before it actually gets written out to a DLL file and linked back in. So this does take a little bit more coding because you have to set up the types. It doesn't support everything. So you have to think sometimes about the way to code things. And unlike my beginner advice of avoid low-level code, you may find that things that can be made faster by writing low-level code, but in order to make it amenable to compiler. And this is a big long-term project for us to improve the compiler, to improve the targets, but also, more importantly, to improve the range of functionality that is compilable within the language. Now, the types there, you saw me use, let's see, what did I use in that? I specified in the code that the argument was going to be a machine-size real number, so 16 decimal places of number, and that the counter was going to be a whole number up to 64 bits in size. But there's a whole collection of these things. They're mostly the kind of things that, if you are used to lower level languages, that you that you would concern yourself with. So different sizes of there's specialist types like Boolean and string, different sizes of integer and real, whether they're signed or unsigned. So are you going to expect positive or negative numbers? If you use, if you use too small a size word, then this is now kind of a problem you have to concern yourself with. In regular Wolfram language, you don't have to concern yourself with having a counter that is 32 bits in size and might overflow if you count to a too big a number. But when you're in the compiler world, you now have to start thinking about the consequences of the decision of real 32, which can't hold as big a number, or unsigned integer, which is very small and fast, but can't hold negative numbers and can't hold a number above above, I guess, 255, I guess, is going to be its largest number, and so on. There's also, if you are a C coder, then there are a whole collection of native C types, particularly important if you're going to write code that links into C libraries that you've already written, for which we have some technology. And then on the top of that, there are some composite types that allow you to deal with things like arrays. And again, depending on whether they're packed, regular, numeric, sparse, or some kind of uniform list. So here's, for example, how you would write something that takes a list of numbers is function compile of a function with an argument. And our argument is going to be a packed array of 64-bit reals of dimension 1, i.e. a list of numbers. And in this case, all it does is do a cumulative addition of those numbers. So if I compile that, it can now understand that there's going to be arrays involved and will handle that correctly. So here's our cumulative total of the numbers from 1 to 10. I guess this is getting a bit boring now that by this point you'll expect, of course, that is faster than trying to write the thing in pure Wolfram language because of those compilation improvements. Now, also, the other type of data structure that you can support is the data structures that that we had before. So actually, this example just uses these clever data structures, but they're fully supported by the compiler. And in fact, I can declare in the type information that, for example, it's going to expect a data structure of type Q to be coming to it as the argument. So we can pass these data structures around these compiled functions. So all of that specialist data structure technology is all entirely integrated with the compiler as well. I won't bother running this one. I said also that it gave you some kind of advantages as a developer, and actually, surprisingly, it's when it goes wrong, as it were, when it throws errors, that's when it's being useful to you. So in this first example, it's come across a symbol that it doesn't understand what type that is going to be, and it can't infer it. And so that's a hint for you to go back and give it more information, or that you've made a mistake because you are mixing two types that were not meant to be joined together, like you're adding a real and a Boolean. And like actually, in this case, is a more explicit example of that, where I've got a type Boolean and I've asked for sign of a Boolean. Well, that's not meaningful. So I've got confused here about my data. So this static type declaration can also be used as a way of doing static analysis and debugging your code, because almost certainly I've written this code wrong. I meant sign of something else that is expected to be a real or a complex or something, but not a Boolean. So the fact that it cannot find a definition for how sign will handle Booleans is a sign that I've made a mistake in my typing. It is also the error you'll get back if you try to use some very high-level function within the Wolfram language, like symbolic integration, that doesn't yet know how to be compiled. So that there is a second meaning for that error, which is simply cannot find a way of doing this because we're at the limits of what we've developed in the compiler. Hopefully, over time, that side of that message will go away. And give you the reminder of the key things as a beginner: fewer functions is better. Higher level functions is better. Don't try and write low-level codes. Don't index items one item at a time across an array or a list. Try and use the data objects with functions that handle them as a whole. So functional generally better than procedural. It's not intrinsically true, but generally these kind of procedural things end up leading you into indexing item at a time, which is a bad thing. There are special data structures out there. There is parallelization and there's compilation, but don't forget the biggest one, which is floating point numbers soon and throughout. If you're doing numerical computations, don't use integers unless you care about exactness.